Hello viewers. So till now we have learned how to analyze under reinforced and over reinforced and balanced sections of RCC beams. Now let us perform an interesting thought experiment where we are going to provide reinforcement on compression side along with the reinforcement on tension side. So today we are going to discuss the effect of this compression reinforcement on moment carrying capacity of a beam. So let us say we have a beam of effective cross section 230 by 500 mm. Again, by effective cross section I mean the depth that I am prescribing is effective depth and not overall depth. So let us say we have a beam of cross section 230 mm by 500 mm and it is reinforced with 3 bars of 12 mm diameter, 12 mm diameter on tension side. We have already solved this problem and we know that with this tension reinforcement, the section is going to be under reinforced section. Cu will be equal to 0.36 FCK. Let us say the grade of concrete and steel that we are going to use is M20 and Fe415. So for this grade, 0.36 into FCK into B, that is 230, into XU. XU is the position of neutral axis from extreme compression fiber. This is XU. This must be equal to TU, which is equal to 0.87 Fy into AST. AST is 3 numbers of 12 mm diameter bars. Therefore, it is going to be pi by 4 into 12 square. If we equate this Cu and Tu, we get the position of neutral axis or we get the value of Xu. So that Xu turns out to be 74 mm. Now recall we have already solved this problem earlier. So I am not going to go into every detailed step of the solution. So let us write down what is the value of moment of resistance of this section. This we have already calculated and it is equal to 57.46 kilonewton meter. The explanation of this value, its calculation, everything is explained in this video. So MUR for this section is 57.46 kilonewton meter. As the section is under reinforced, bending strain distribution diagram at failure is going to look something like this. The strain in steel is going to be greater than yield strain when the extreme compression fibers reach the strain value of 0.0035. Now, in addition to this tension steel, let us try and provide some compression steel. So let me provide 2 bars of 8 mm phi as a compression steel. Now please understand that this is purely a thought experiment. We will see later that these 2 bars provided as a compression steel are called as anchor bars and we cannot have their diameter less than 12 mm. But for time being, let us consider that we have provided compression steel as 2 bars of 8 mm diameter. And let me say that the distance of centroid of this compression steel from extreme compression fiber is 40 mm. So this distance is 40 mm. Now with this compression steel and looking at this bending strain distribution diagram at failure, let us try and write down the compressive force. Compressive force at failure now is going to be the summation of compressive force provided by concrete plus compressive force provided by steel. I am going to call these contributions as Cu1 and Cu2. So let us try and write down the expression for Cu1, which is the ultimate compressive force provided by concrete on compression side. So that value is going to be equal to 0.36 FCK B into XU. XU needs to be evaluated. The position of neutral axis from extreme compression fibers needs to be evaluated. Now you have to observe here that when we provide the compression steel, we have taken off the equal area of concrete. Therefore, this Cu1 provided by concrete is overestimated because we have to consider that some of the concrete portion has been removed to make space for compression steel. We will take care of that in Cu2. So what is the value of Cu2 that we will be writing? Cu2 will be stress in steel. So let me write it as FSC, which stands for stress in compression steel, multiplied by area of compression steel minus stress in concrete at the level of this compression steel. So that I will call it as FC. So what is FC? FC is the stress in concrete at the level of compression steel multiplied by area of concrete which is removed. So that area is same as area of compression steel that is provided. So I will write it as FSC in FC into ASC. But you will understand that this compression steel is provided very close to extreme compression fiber. So strain there is going to be somewhere between 0.002 to 0.0035, and therefore the value of stress there is going to be equal to 0.446 FCK. 0.446 FCK. So therefore I can write Cu2 equal to FSC minus FC, which is 0.446 FCK, multiplied by ASC. I hope I am quite clear on this. So what is the total value of compressive force addition of Cu1 plus Cu2? Now the problem here is we don't know the value of stress in compression steel. And unless we find out XU, we will not be able to find out strain at the level of compression steel. And as the strain at the level of compression steel is unknown, therefore we will not be able to find out the stress at the level of compression steel or stress in the compression steel. For this analysis now needs the iterative strategy. So I will assume with the iteration number 1. So I will call it as I1. Iteration number 1 is I will assume FSC to be the maximum possible value in compression steel, and that value is 0.87 F1. So let us assume that FSC is equal to 0.87 Fy. Now if I substitute this 0.87 Fy as FSC, 0.446 FCK as FC, area of compression steel is already known. It is 2 times pi by 4 into 8 square. So I can write down Cu as 0.36 FCK B XU plus 0.87 into Fy minus 0.446 into 20, this multiplied by area of compression steel. But area of compression steel is also known, and that is 2 into pi by 4 into h square. Tensile force now can be written as tensile force now can be written as 0.87 Fy into area of tension steel, which is 3 times pi by 4 into 12 square. For equilibrium, if I equate now Cu and Tu, I will get the value of Xu. So let us find out that. So Xu works out to be 52.59 mm. Now once we know the value of Xu, now in the same iteration we can compute the strain at the level of compression steel. So let us work out what is the value of strain at the level of compression steel. We are going to consider these two triangles as similar triangles. So as the value of Xu is 52.59, this value is going to be 52.59 minus 40. So it is going to be 12.59. So let us apply now similarity of triangles, and what we get is strain in compression steel divided by 12.59 must be equal to 52.59, which is Xu. 52, sorry, must be equal to 0.0035 divided by Xu, 52.5. We are applying similarity of triangles between this triangle 1 and this triangle 2. So by that similarity of triangle, I get epsilon SC or strain in compression steel to be equal to 0.0008. Now we are going to ask ourselves a question. What is the value of stress corresponding to this strain in Fe415 steel? So I will have to go to stress strain curve of Fe415, and I will have to work out what is the value of stress at the level of 0.0008 strain. FSC turns out to be equal to 250 MPa. What is the assumed value of FSC? 0.87 Fy. That turns out to be 0.87 into 415. 0.87 into 415 which is 361 MPa. Therefore, the iteration fails. This value is less than 361 MPa, which is assumed, and therefore this iteration fails. So let us begin with the second iteration, where we will now assume FSC is equal to 250 MPa. So iteration number 2, we assume FSC is equal to 250 MPa. So let us find out the position of neutral axis. So CU, that is 0.36, FCK, B into XU plus FSC is now 250 multiplied by ASC pi by 4 into 12 square into 2. So therefore compressive force 0.36 into 20 into 230 into XU into 250, which is FSC, minus 0.446 FCK into ASC, that is pi by 4 into 12 square, pi by 4 into 8 square into 2. This must be equal to 0.87 Fy AST. With this, now let us try and find out what is the value of XU. So now XU turns out to be 60 mm. For this value of XU, now let us find out the value of, now for this value of XU, let us find out the value of strain in steel on compression side. So again, we are going to apply similarity of triangles. This is the first triangle. This is the second strain triangle. So we get 0.0035 divided by XU, that is 60 mm. Therefore, by similarity of strain triangles, 0.0035 by 60 must be equal to strain in compression steel divided by, now this distance is 60 minus 40, that is 20. So divided by 20. So if I solve this, I get epsilon SC to be equal to 0.0011. 0.0011. For this, the value of stress in steel is equal to 270 MPa. Which is now slightly different than the value of FSC that we have assumed. Now we will have to go on doing these iterations. Still, this FSC assumed and FSC calculated turns out to be same. So we will have some criteria and then we will stop doing the iterations. We will say that the solution is converged. For time being, 270 being not very different from 250 MPa, we will stop our iterations here. And therefore, we will say that the XU is at 60 mm. So we have got the first result. First result is, if I provide this compression steel, the XU, that is neutral axis at failure, is going to be at a distance of 60 mm from extreme compression fiber. We can readily compare this with XU without compression reinforcement. So as we can see, by adding compression reinforcement, XU has been reduced, or neutral axis has been shifted towards the compression, extreme compression fibers, and therefore the degree of under reinforcing increases. The section becomes even more under reinforced by addition of compression steel. So our first observation is, by adding compression steel, I take neutral axis at failure above, and therefore the section becomes more under reinforced. Degree of under reinforcing increases. Now let us work out moment of resistance of this. Moment of resistance of this cross section with compression steel provided will be equal to Cu1 into its lever arm, Cu1 into its lever arm, plus Cu2 into its lever arm. Now you have to observe one thing, Cu1 and Cu2, they act at different locations. Cu1 acts at 0.42 XTU from extreme compression fiber has already been derived. So therefore I will show this. Cu1 acts at 0.42 XU. This we have already derived. Whereas this is Cu1. Whereas Cu2 acts at the centroid of compression steel. So Cu2 is going to act at distance 40 mm from extreme compression fiber here. However, the tensile resistance to both Cu1 and Cu2 is provided at the level D from extreme compression fiber. Therefore, lever arm with Cu1 will be equal to D minus 0.42 XU whereas lever arm with Cu2 will be equal to D minus 40 mm. D minus 40 mm. So now let us write down this expression for MUR. So MUR is Cu1, that is 0.36 into 20 into 230 into XU now is 60 mm into lever arm, which is 500 minus 0.42 into 60 mm. Cu2 is FSC now is 250. So 250 minus 0.446 FCK, which is 20 multiplied by 500 minus 40. So if I substitute all those values here, I get moment of resistance of a section in presence of compression steel equal to 58.32 into 10 power 6 Newton mm. So to convert it into kilonewton meter, I will have to multiply it by 10 power minus 6. So it becomes 58.32 kilonewton meter. So what do we observe? This moment of resistance, ultimate moment of resistance of cross section in presence of compression steel along with tension steel is marginally more than moment of resistance of a cross section without provision of compression steel. So what is the effect of compression reinforcement on moment of resistance of a section? There is marginal increase in moment of resistance. And the second effect of compression steel is it takes the neutral axis above. Therefore, cross section with compression steel is more under reinforced than the cross section without compression steel. So with this effect of compression steel in mind, in the next class, we are going to begin with the analysis and concept of doubly reinforced sections. So let us stop here today. Thank you.